We would like to end this series on problem 8, which is a more open-ended question about geometry, in particular, regular polygons. Find all positive integers n greater than or equal to 3 for which a regular n-gon can be perfectly divided into at least 2 possibly different regular polygons. With these questions, my number one tip is always start with small examples to get a better grasp of the problem. For example, how do we tile or divide this regular S3E8 or equilateral triangle with smaller polygons? Well, a good idea is just to start from the corners. We can add like triangles, for example. Maybe you want to add a triangle here. Maybe have a triangle here. Oh, I'm already seeing where this is going. With just a bit of experimentation, we could do something like this, right? 3 triangles and a regular hexagon. Or maybe one other possibility is to draw this sort of Zelda Triforce sort of thing. We have these 4 triangles that are all equilateral. As you can see, indeed, these are all actually congruent triangles. But you can see that n equals 3 works. How about 4? This one should be pretty easy. It can be just divided into smaller squares as follows, right? Just dividing it in half twice. So 4 works. Let's do 5 now. Is it possible to tile this regular polygon, this regular pentagon? Well, let's think about, again, starting from the corners here. Well, what is this interior angle? Do we know? Well, it's just 180 degrees times n minus 2. That's the total sum of the angles in any n-gon. And divide that by n for the number of vertices, because they're all the same measure. This gives us 180 degrees times 3 over 5. In this case, 108 degrees. Okay. So what can we do? Well, we might think about, okay, within this region here, we can maybe fit a triangle and a square. Okay, this doesn't really look like that, right? It looks like we can't fit a triangle and a square. And actually, if we try to fit 2 triangles, that's even too large, right? Because if we have a 60-degree angle of the equilateral triangle, in the 60-degree angle, that's not good enough, right? We're going to end up with something like this, and then it's just going to overextend like that, right? We're not going to be able to jam 2 triangles into that to share that corner. So it actually turns out that, well, triangles are the lowest angle shape, right, that we can possibly make with regular n-gons. So actually, any 2 n-gons crammed into that corner will simply not fit into the 108 degrees. So it turns out that we can only fit at most 1 polygon in that corner. And in order to fill it efficiently, we need to make sure that itself is a pentagon, right? Just like that. So if we try adding this, of course this pentagon in this corner cannot be just simply the entire shape because we require it to be divided into at least 2 other polygons. But as you can see here, that leaves this sort of awkward shape that we can actually prove cannot be tiled, right? In particular, we always start from the corners. 72 degrees here. Well, 72 degrees is once again awkward because a square already has a degree measure of 90. A triangle, well, 2 triangles certainly has greater than 72 degrees. And if you put a triangle in there, that's your best bet, right? Well, we only have 12 degrees left to work with. So clearly, no 2 triangles or no 2 polygons can fit in that angle, and no single polygon can fit either. So actually, this tells us that the pentagon just simply doesn't work due to that sort of angle idea. Okay, so 3 works, 4 works, 5 doesn't work. It doesn't work. How about 6? Alright, so hopefully we'll have better luck with hexagons since they have better angles of 120 degrees. We can actually pretty quickly see that we can fit 2 triangles in every corner as follows, right? Just having an equilateral triangle in 2 equilateral triangles in each corner, which forms this very common sort of tessellation of a hexagon with 6 triangles, right? So this also works. Yeah, so that basically tells us that, okay, well, 6 works. How about numbers greater than 6? We have a feeling that, 7 probably won't work because 7 is a weird number, and so on. But how do we sort of generalize this pattern we've seen? Well, what about a really large n-gon like this, right? If we can imagine the angles being like this, which are like 180 degrees, almost like very slightly less than 180 degrees. How do we fill that up? Once again, we start with the corners. We can quickly see that since the interior angle is always less than 180 degrees, right, we know that that must mean that we can't fit 3 triangles in that corner. In general, we can't fit 3 n-gons, right? Any three regular polygons will not fit. Like a triangle, a square, and a triangle still will be too much, right? Because our smallest possible total angle of 3 interior angles of 3 regular polygons is greater than or equal to 180 degrees, right? 360s. Which just means that we need to fill each corner. It has to be shared by either 1 or 2 angles, right? In particular, if we just jam one angle in there, well, then the problem is that you will end up with this sort of problem, right? Where you have the n-gon and then you have a smaller n-gon, but that leaves this really small angle, which certainly cannot be tiled, right? In particular, for large numbers, this is like almost 0. So you can see that basically we're definitely not going to be able to fit even a triangle in that that gap, which tells us that this tiling is impossible. Okay, so then our only possibility is to fit basically two shapes inside. So maybe like a triangle and another triangle, so that gives us 120 degrees, a triangle and a square, right? What else is possible? This is 120 degrees. How about a triangle and a pentagon? So that's 60 plus 108, 168. A triangle and a hexagon. Oh, okay, we can see that that's 180 degrees, right? 60 plus 20. So this is disqualified. With a triangle, we can only fit another triangle, a square, or a pentagon. With another square, of course, we can fit the triangle, but we already knew that. And then, obviously, if we have a pentagon, that angle is too much. So, we can't fit 2 squares in a corner because that would be a total of 180 degrees, and we know that every regular polygon's interior angle is less. So, actually, these are the only 3 possibilities for putting 2 regular polygons in the same corner. And in particular, these actually all correspond to proper interior angles of the following shapes. This is the hexagon, as we saw here. This is 150 degrees is for, well, when is the interior angle 150? Another way to think about interior angles is 180 minus the exterior angle. So if the interior angle is 150 degrees, then this is 30 degrees. And we know that the sum of the exterior angles as we walk around the polygon is 360 degrees. So we're just asking for what n is 360 over n equal to 30 degrees, and that's for n equals 12. So n equals 12 is a possibility, and then similarly, if we have a 168 degree angle here, then the exterior angle is 12 degrees, which tells us that 360 degrees over 12 degrees equals, over n equals 12 degrees, which tells us n equals 30. Since we've already shown that 6 works, the only 2 remaining numbers that are possible are 12 and 30. So let's just quickly erase some of this so we have more room to work. Alright. So let's first consider the 12-gon. The 12-gon looks as follows. We know that every corner has to contain exactly one of each of a triangle and a square. So if a regular 12-gon looks something like this, then, for example, we can put a square like this, and then a triangle here, and a triangle here, and then we can put another square like this, and we can continue around the 12-gon like this, right? So we can see that after we do that, a nice shape in the middle emerges. Wait, this is just the regular hexagon, right? If you're not convinced, we know that all the lengths are the same. And if we look at the missing angle here, 60, 90, and 90, well, 90 and 90 make 180. So 60 and this last angle add up to 180, giving 120 degrees. So in fact, this is indeed a regular hexagon, which tells us that this regular 12-gon has been successfully dissected into 6 triangles, 6 squares, and a regular hexagon, and that gives us n equals 12 works. So 12 works, and the only remaining possibility now is 30. Okay, so 30 seems like it could be possible, as suggested by the sort of analysis with 2. But we might run into an issue because of those pentagons, right? We've initially discussed how pentagons might lead us into trouble. For example, in one corner here, we might put a triangle here and a pentagon here. It is also possible to put the triangle on the entire edge, but what we really care about is sort of this angle here. Well, in this angle, well, it's 72 degrees, and as discussed previously, 72 degrees cannot be properly tessellated, right? It cannot be filled by polygons. So actually, this pentagon here that I've drawn has to, the only chance for it to work is if it spans the entire thing, and then the triangle follows suit, right? Similarly, every pentagon has to basically fill the entire edge here. Otherwise, it leaves that awkward 72-degree angle, which gives us 108, 108, right? So all the angles here add up nicely. And now let's just consider this remaining angle that is formed from these 3 other angles. With 108, 60, and 108, those add up to 108 plus 108 plus 60 equals 236, or 200. These add up to 216 plus 6, 276, which leaves a total of 84 degrees out of the 360 to be filled. However, we can see that 84 is very small. It is in fact less than 90, so we can't put anything better than triangles in. And similarly to 72, we can't fill that with just triangles either. So in fact, we've reached, once again, a dead end, which results in us not being able to tile this 30-gon. So in fact, similarly to the pentagon, the 30 falls, and we only have 6 and 12 out of this group, which tells us that total we have 3 works, 4 works, 5 doesn't work, 6 works, and 12 works. So our final answer is 3, 4, 6, and 12, and no other possibilities. QED.